Today is the day we conclude once and for all Material Balance section, chapter 4 for elementary principles. That's a long sentence. Chapter 4 will be done today. I will discuss the examples that couldn't come to any instructor in the world because I want to conclude this chapter in a very nice and difficult way. We will start with single reaction but with equilibrium, which is the concept that we haven't introduced so far. And then we will move to multiple reactions. Lastly, we will have something really interesting to say at the end of this video. Let's go ahead and start. We have a reversible reaction or equilibrium reaction of a batch system receiving this amount of mole of oxygen and sulfur dioxide, and it will react to make sulfur trioxide. We are asked to find which one is the limiting reactant and what is the maximum percent conversion in addition to the outlet stream in this case. As always, when we have a material balance, regardless physical or reactive, we start with a flow chart for this batch system, and then we do degrees of freedom analysis. But for the reactive system, we ask ourselves, do we use atomic species or extent of reaction method? If you have a reversible reaction, you will depend on the extent of reaction method. Otherwise, you will depend on the atomic species, regardless if you have a single reaction or a multiple reaction. Having said so, and we chose extent of reaction, we will have three unknowns. We will have 0 independent chemical reaction and 0 independent non-reactive species, but we will have 2 independent atomic species, which are the sulfur and the oxygen. The new relation that we haven't introduced so far is the equilibrium constant. It can be used as an additional relation inside the degrees of freedom analysis: 3 minus 2 minus 1, ending up to have a 0, which means we can solve the system. The equilibrium constant equation is the product concentration divided by the reactant concentration, keeping in mind that we have a corresponding stoichiometric coefficient, so the concentration will be to the power of half. Now go back and use the extent of reaction equation. If you used mathematical manipulation, you can reach to this expression. Substitute it back in the equilibrium constant equation. This is to eliminate all the different number of unknowns and to end up have only just one unknown, which would be the extent of reaction for the limiting reactant. The limiting reactant will be the sulfur dioxide. We established this equation, and now it's not our job to manipulate this equation further to reach to the form of ax squared plus bx plus c. We need to use the calculator to find out the answer because we are chemical engineers, not mathematicians. Unfortunately, your calculator has to be fxes plus. Otherwise, if you use another calculator, you will not find the calc button. If you construct your equation, then find the x value if you press calc. This x value represents the xi we wrote in the equation. Do that iteration over and over and over again until you find the number that will be the k, which will be 8.5. You use this xi to find what we call a very important terminology: equilibrium conversion. And remember, the maximum conversion we can reach in reversible reaction is the equilibrium conversion. The maximum conversion we can reach in an irreversible reaction, it will be 100%. As for the way we calculated this maximum percent conversion, it will be using the following expression. And if you did find the equilibrium conversion, you can find the product composition. One last thing we need to do is to find out the total amount that came inside the batch reactor and the amount that left outside of the reactor. They don't have to be equal because we are talking about the total amount of moles and not the total amount of mass. And indeed, the total amount of mole came, it's not the same as the total amount of mole leaving. It's actually higher than the moles that will leave. And this can be explained by this following expression, which we will cover later on in reaction engineering. Fischer-Tropsch process is used in industry heavily when we want to convert carbon monoxide and hydrogen gas. In the second paragraph, it describes that we have a feed of unknown stream and we have a product of unknown stream, but given two products which are butane and pentane, 12.5 and 22.7 respectively. From the product streams we are asked to calculate the feed streams in addition to the remaining product streams, keeping in mind that we have a reaction producing multiple products. It's not a selective reaction. The flowchart, degrees of freedom, because it's not a reversible reaction, we can use atomic species. It's better to use atoms because they have the rule of moles in equals to moles out, making our life much easier. Doing so, we will have 3 independent atomic species, which means 3 independent equations. Problem is, we can't solve. We need 2 additional equations, which will be the 2 conversions of the hydrogen and of the carbon monoxide. We'll start with the carbon monoxide conversion, single pass conversion. We will find the carbon monoxide entering, and we will from that find the mole stream that will leave. We will do the same exact thing with the hydrogen. We have its fractional conversion. We can use it to find the in and out of the streams for the hydrogen. Doing a final check to see the total molar flow rate that will come and leave out of the reactor, we can see that the total stream leaving is lower than that entering because of the shrinkage that came inside the reactor, which will be explained in reaction engineering. You're not expecting us to finish with these 2 problems and without explaining why the heck did we do many decisions without explaining them. What does batch mean? In batch system, you don't have inlet and outlet streams, and you don't have streams, you have amounts. They come and leave, but not during the reaction. Whatever you saw in the problem, when we have in and out, it means before the reaction and after the reaction finish. But during the reaction, there are no feed and there are no products. When you have batch system, you are more likely to see equilibrium reaction. The likelihood of seeing an equilibrium reaction in a continuous system is very rare. It is really slim because there will be many complex reactions to be faced. The third thing about the batch system, why did we choose extent of reaction instead of atomic? If you chose atomic species method, in the reversible reaction or batch system, you are more likely to face 4 equations and 4 unknowns. How can you solve 4 equations with 4 unknowns? You can use MATLAB, you can use Aspen, you can use Excel. The idea, you cannot solve it by hand, otherwise it will take you the whole semester to finish the problem. That's why we make everything in one unknown and then we solve it. And the one unknown was the extent of reaction. In the equilibrium equation, we didn't explain why did we write the product concentration divided by the reactant concentration. It is basically a formula we took in general chemistry. We can express the concentration of the product and the concentration of the reactant in an equilibrium equation if the reaction reached equilibrium, and again, you don't see equilibrium reactions in continuous system. We could have solved the system using the general formula, which is ax squared plus bx plus c, but this will take too much time for you to solve, and you will not be credited for the points in the exam if you solved it using the general law or if you solved it using the calculator. The most important thing is that you know how to find the answer, and the answer must be justifiable. And the calculator can be used to justify the reasons for having the answer. I did emphasize in the 2 problems that we don't have to have equal moles. Remember, total number of moles are not conserved in the reactive system. It could be equal and it could not be equal. It depends. And the reason for having this equality or non-equality is, as I explained before, because of what we call expansion or shrinkage factor that we will discuss later on in reaction engineering. But the total mass, if you have a reactive system or non-reactive system, they have to be the same. As this video explained, total mole is consumed or is generated. And lastly, we wanted to talk about the recycle. Why do we have to do recycle stream, and why do we have to do purging stream? Recycle basically indicates that our conversion, single pass conversion, is low, which means we need to recycle more and more amount or stream of the limiting reactant or of the reactant in general to use it and maximize the production rate of the desired product. That's why we use recycle stream. Otherwise, why do you have to have a recycle if your single pass conversion is 100%? But the problem, it is not practical. The other scenario is the purging stream. Why do we have to purge some little portion of a product or a recycle stream? And the reason is we sometimes could have inert. We could have something that jeopardizes the steady state assumption. And if you recycle more and more of the inert or more and more of an undesired product, the chances that you will keep increasing the reactor concentration inside, it will generate accumulation, and then you won't be having a steady state assumption. That's why you do some purging to make all the material balance analysis under the umbrella of steady state. I skipped one scenario we didn't discuss, which is bypass, and it is literally the opposite of recycle. You make a portion of the inlet stream, and the reason could be because the reactor capacity is small, so that's why you don't make the whole feed enter to the reactor. Otherwise, you can use the bypass stream because you want to do sensitivity analysis. You want to see what will be the effect of the inlet stream on the product stream if it didn't come to the reactor versus if it did come to the reactor. So you want to do some sensitivity analysis. I hope I didn't forget anything about this chapter because it is really the fundamentals of any chemical engineer. You will face it in your life as an employee, not just as a university student. These things that we take so far are not just a toy that we just remember and then forget later on. That's why I keep reminding myself and you that 90% of the undergraduate courses in chemical engineering will be used heavily when we become employees or when we start our own business. We will use it. And with that, we concluded material balance section, and we completed 1 year since we opened this channel. Hope I continue more, and hope you support me as well with the subscription, with the likes, with the views, so that I continue more and more. Because right now in this year, I'm hoping to expand my portfolio, not just chemical engineers, but also engineering videos, personal experience that came in my life, how did I reflect to them, and what is my advice to you, to the young engineers and young people in general, and also the elder people, so that they don't get mad at us. And we hope to see you in the next videos as well. Stay healthy.